Our topic is binary search tree. What is binary search tree? Before we are going to our problem statement, searching a particular node or a deletion from a binary search tree. First, we give a definition for a binary search tree. Not empty. The tree must satisfy these properties. The first property is the each node have a key field, and the keys representation for those nodes are distinct. And second one, the left side of the root is having values less than the key value of root, and the right side, the root, the key values on the left right side are greater than the key values of the root. For example, 40, 30, 50, 20, 35, 45, 55. This is a binary search tree, and it also a complete binary search tree. See here, the first root node is 40, and this left side all keys are smaller one, 30, 20, and 35 all are small than 40, and on the right side all are greater than 40, 50 to 55, 45. Okay, how do we construct a binary search tree? By a set of given values: 1, 2, 3, 4, 5, 6, 7. Let's take this as an example. First we start with 1. Next key is 2. 2 is greater than 1, so we're gonna make a right subtree. Now next 3. 3 is greater than 1, and it's also greater than, so 3. It will form a skew tree, skewed binary tree. By node with a key of 20. So first it will check whether 20 is greater than or 30. No. If it is not greater than 30, so it traverses to left and make a node 20. Similarly, if 40 is greater than 30, so it traverses to right, and now we need to write a C function for this, for inserting or creating a node. So first we write a code for create tree node create for specific node root. So two arguments we are passing, and int n. Int n means number of nodes in a binary search tree. Int I. Okay. Next int e. Okay. Next we are applying a for loop for I is equal to 0, I less than n, I plus plus. So printf statement for entering the key for a node. First, at this moment we just concerning the key of the node, nothing we are considering here. Scanf %d and %n and %e. So now we are calling a function root is equal to create tree root comma n, root comma e. So that key value we are transferring it with an as an argument to the creative function. At last we are returning the return root. First initial condition, root is equal to null. If root is equal to null, so it will process this for loop, or else it will print the tree has already some data. Okay, now it will return root because it return a node type. Node type data, so root is of node, so we are returning a node. Next, this is an create function. Now we are going to write the implementation of create tree function. So next is node create tree. It will take two arguments, node p comma int e, so root and e. So here node p, node e. So first initial condition, if p is equal to null, so directly we need to insert this. So malloc, we're gonna call malloc p size of node comma n. So malloc p size of tree comma node. So p signifies the actual memory we want to store in p, and the next variable to store that size, referring that size, that memory allocation. P is located to that particular memory location, and the size of tree, structure tree. Okay, the memories, whatever the we defined as struct tree, so that amount of memories, a block of memories allocated to p, and which is we are converting that type into node form. Okay, we are writing implementation, and p info means information, or you will either take key also. P info is equal to e, and p left is equal to null, p right is equal to null. Okay, next up is just okay, else if p is greater, if e is greater than p info, so we need to traverse p right side, similar to this 40 next 50, similar to this. So p right is equal to create tree p left right comma int e. So else if e is less than p info, so we need to traverse to the right. Left is equal to create tree p left comma int e. So or else there is only option, if e is equal to p info, we need to print duplicate entry. At last return p. So it's a simple C function for create tree node. So first using create, we are sending a data to each node, and using create tree we are creating the tree. So our second point is to traversals. So first I will show how our this function will work using an example. First we are entering a data of 40. Take example of 40. Okay, first we are entering 40 node, entering a 40 key, and we need to traverse to the left. If a user entered, I think take example of 50, so 50, so here he entered 50, so this function is called, so it will traverse to here. P is equal to null, no, at each time. So it checks PE 50 is greater than P info, yes, it will traverse to P right. So now P is pointing to here, and create tree P right int E, it's again calling a function P right. So now our traversal is here, we are pointing here. So next it's P is equal to null, yes, P is equal to null. So it will allocating a memory and creating a node. So here 50, next will come 45. Let's make a complicated one, easy to understand. Next P, so again P created tree root E. So again we are going this malloc. First we are checking whether the root is here. P is now pointing to here, P is equal to null. So now it will traverse to the left one of this P null, so 45. How it works means, here P will check whether the key is greater than 45. No, it is less than 45, so the P will traverse to right. So again it will check, P is now pointing to 50, so 50 is greater than 45, true, so it need to traverse to the left side, and there will again we are calling recursive function create tree node P. Now the P is equal to null, so malloc function will call and create a node here 45. Similarly, now take example of if a user enter 20, 40 is greater than 20, so we need to go left side. So left side P is equal to null, so this recursive function, after calling this, the recursive function will stable here and create a node. New node is 20 and its root is 40. Our next topic is traversal of binary search tree. So for traversing of a binary search tree, there are three methods. First one is post order, and second one is pre-order, third one is in order. So as you know, post order is the root node is written at last, it will like left, right, root. Similarly, breathe, root, left, right. In order is left, root, right. Okay, first I will write wide post order node root. Okay, if root is not if root is not equal to null. Okay, first we need pre-order, first post order we are writing for. So first root need, we are writing a recursive function for this. So post order root left, post order root right. Then need to print the actual value, root value, root info. We are taking info similar to this pre-order, wide pre-order node root if root not equal to null. First we need to print the actual data, so root info, and then we need to traverse first at a left pre-order root left, pre-order root right. Similarly, wide post in order, last one is in order node root if root not equal to null. First we need to traverse at left printf percent root info, and next we need to traverse right side root right. Similar, I will take small tree to explain each one is how they go work. 30 20, no, I wrote 20 50 40 20 50. So post order, first it will check root is not equal, yes it's not equal to root. First it will traverse left, so I extend this to better understanding. 15 30, so first it will traverse to the left 20 15. So then it checks whether the root is equal to null. Yes, null. Now so it holds here, the function holds here, and it traverses back to the function, and it will check it's a root. Next it will traverse to the right after 15, so it's also null. So root waits, so halts here, recursive function halts. Next it will print 50 because it's a root, and next it will traverse back to 20. How that recursive function will work, I will write a stack representation. So first 40 will be at where pushing it, and next 20 because we are traversing left we need to push all the things, and next 15. After we are 15, now the root is equal to null after pushing the 50, so it will come back. to 15 and it will try to traverse to the right. The next one, root right. So then also there is no data, so root is equal to null. So after this 15 it will pop root info 15, so and it will print 15. Next after 15, so it again traverse back that the 20 function, the 20th node, and it will traverse to the right side. Again it will print 20. Again it will push 30, not 20. It will not print 20, it will push 30. Now the top is 30, so again the root is equal to null, so there is no operation going to take place, so the 30 will be popped out, so 30 will print. And next, now again traverse back to the 20, now it will pop and we're going to print 20. And similar to this way, again we are going to 40, traversing back 40, and there is a right post order root right 50, so it is pushing, so now 50 40, so 50 we are popping 50 because there is no left child and right child, so again 40 is popped, so 15 30 20 50 40, it's a post order of a binary tree. So better understanding, I will show a binary tree representation how that post order worked. So first I will represent first post 40, post order 40, the function call like this, root means 40, so 40, so the function root is not null, so it will call post order root right left, so the tree will traverse up to left like this, 40 20 15 30 and 50, so the tree now traverse to 20, so post 20, see the another two function is not still executed, now the tree post 20 is called, so again it will check post root is not null, so again it will call 15, post order 15, so after it will call post order, so it will traverse to, still it's not holding, next one will be null because there is no null, because there is no data, so it will call null, so function halts here null, so it will return back to here post order, so post order as we completed left, next of this function post order left is equal to null, next post order 15 right, we call this function 15 left, left is not, it is null, so now right it's also null, so at last this function will print f %d 15. So what is that root info, so root info is 15, so it will print 15 like this. Now the post order of 15 that we called it in post order of 20, now the second step what we have, post order of 20 is left right tree is 30, so now the second step starts, we write post order of 30, now we are writing this function, this recursive functions implementation, it will return null both post order write null. At least it will print that root info, both are null. Here also both are null. Okay, now we come to the actual 20 where the last line is printf, so it will print 20. So again we are only the first line of 40 is implemented, remaining line post order root write. So this will implement which is called by 40 this function. So 50 post order of 50 where both statements are null. So 50 is print function is called, and last 40 the last printf is called. Like this the stack operation for post order takes place. Similarly the pre-order is also same to same. In order, try to trace that stack representation for these, how the stack function works. Okay, next topic is search. We need to write an search function for a particular key. It's a similar to an inserting function. We need to check, we need an function int search node root comma int key. So that particular key we want to search, that is there is a that the key is there in that tree or not. So for that function, if root is equal to null, we return null. If root info is equal to key, we write keys found. Or if root key is less than root info, return recursive function return search node root left comma int key. Okay, or else return search node root right key. That's it. So if a root no info is equal to key, we can key is found. Or else if a key is less than root info, then we traverse to the left side, because when the key is greater than less than 20 less than its node, when a key is less than the root info, the key might be must present at the left side of that particular node, otherwise it need to be present at the right side. That's a simple case. So at last I will explain how the deletion process takes place. First, deleting a node which is there is no left child and childs of that particular node. It's a very simple. Take example 40, 20, 15 and 30, here 50. So deleting the 15, it is very simple, which is having no child nodes. So just deleting it is very simple. So 20 make the root left is equal to null. That's enough. Or else second option is deleting a node who having a one child, like example 40, 20, 30, 15. Deleting I will take and extend this 50 to an 20, 55, 55. Deleting the 50 node, just we need to change this 40's root right is equal to 55. That's enough. No complication here. But actual complication comes when deleting a node who having two childs, 40, 20, 30, 15, 50. We want to delete 20. So there is one option. Either you choose a largest left side value or smallest right side value. So when you are deleting 20, we need to choose a largest left side value. It's 15, so there is no other left. So tree will become 40, 15, 30, 50. Or else this is one option. Second option is choosing the smallest one, smallest left child, 30, 15. It's another possibility.